Verhaven. We work as developers, software developers, at a company called Scientific Volume Imaging. That's a relatively small company. Here is a picture of mostly everybody. Maybe one person was missing or so, but the company is located in Hilversum. And what we do is we make software to process the data from microscopy images. So light microscopy at visible wavelengths. If you think about a microscope, I think many people will have an image like the left one here. That's what a microscope more or less looks like if you have a memory of biology classes in high school or so. Actually, the data is collected with a machine that looks like the image on the right side. Maybe noteworthy to say that quite a lot of the data that we work with is actually three-dimensional, and the software can both handle wide field images, so you are looking just like you would look through the eyepiece, but quite a lot is also acquired with a so-called confocal microscope, where the image is more or less acquired pixel by pixel. Let's see. Why am I not getting? I think I clicked on the presentation. So this is an example of an image, or actually a movie. What you are seeing is a dinoflagellate, so that's a kind of an algae cell, and then you see the microtubules visualized. You see in the red channel the traditional confocal microscopy technique, and in the green channel the equivalent image acquired with a super resolution technique. And this is surface rendering, so in the super resolution technique you can see more details. And well, this kind of animated movie is an example of what you can make with the software in terms of visualizing some results.
What's the scale
actually visible and down is like.
Yeah, here
I see, I can see it.
the scale on the top left says 3 micrometers. So yeah, it is on more or less on a cell level. The normal cell would be an order of 10 micrometers, or at least the central part of it. Well, that's. Go to the next slide. The software is called Huygens. It is named after the Dutch scientist Christian Huygens, who lived in approximately the same time as Isaac Newton, and is known for his contributions to optical theory, like the superposition principle of waves, and some contributions to polarization and a lot of other things. One of the main functionality features in the software where it started with is to do deconvolution on images. Later a lot more was added. The deconvolution, simply said, it makes the image look sharper because it unveils details that are hidden in the acquired data. So if the microscope in the data acquisition does something which is mathematically described as a convolution on the image, and which visually appears like it is a blurring. We try to undo that blurring effect, so you get a sharper image out. That is the deconvolution step. So here you can see some examples of what the deconvolution does to an image. This is the same image that you saw in the movie, where you see a surface rendering of the raw data compared to a deconvolved. And this is an image of neurons, where you see the raw data visualized and the deconvolved compared to it. The software has different ways to visualize data. Usually it is 3-dimensional or 4-dimensional, where there is a time dimension, and then there can be multiple channels, like multiple colors. If you do fluorescence microscopy, you can have multiple fluorescence channels, which are acquired simultaneously. So here you see a maximum intensity projection way of visualizing the data. This is a special way of visualizing that emulates what happens with a fluorescence process. Here you see 3 orthogonal slices through the 3-dimensional data set. So there's different ways to visualize data. This is a part of what the user interface looks like. So you will recognize a lot of TK, because basically everything is made with TK. User interface is, of course, for a software like this, an important part of the software as a whole, because not everybody who is using it, or almost nobody who is using it, is a programmer. They are biologists who want to process their microscopy images. And then, apart from the deconvolution, there's different kinds of things that are not ideal in microscopy images that we are trying to correct. So the lenses act differently on different wavelengths. So you get something called chromatic aberration, which you try to correct for in part in the lens, but any residual chromatic aberration problems you can try to correct in software, so the colors end up shifted relative to each other. The stitcher tool is quite familiar if you think about a smartphone or a compact camera, where you can take these panorama pictures which are stitched together into a single picture. Well, you may want to do that with microscopic images too, then maybe in 3D, but if you have a certain field of view of the microscope, you can move a stage and collect multiple images which can then be stitched together. If the homogeneity of the illumination or the data collection is not completely ideal, you can get something like this. We call it a vignetting problem, that you see the borders. And of course, then we try to correct for this kind of thing too. Then we have a separate tool which is used to manage a huge database of microscopic images. So you can do some searches through the metadata, like get me all the images where the file size is between 4 and 6 gigabytes and which have 3 to 6 channels, etc. That kind of queries. So it can do indexing in the background overnight, and then you have a database. Here you can see an example of where we speed up the computationally intensive part of the of our calculation using a GPU. So on the left half you see a CPU calculation on an Intel Xeon, 4 cores, and on the right side is a graphics card. So these are 2 movies. I will now start them, and they are more or less a real-time recording of what happened. And as you can see, the right one, you see the iterations producing each one line is already finished with the first channel out of 2. The GPU is now already finished, and the CPU is still working on the first channel. So it's a visual illustration of the speed up that you get. So this concludes the first part of the talk, the general introduction to the software that we make. I would now like to give the floor to Paul for more details on how we use Tickle and TK.
Good morning. Indeed, like we said, like who are we? Now we are like more like what do we do with Tickle and TK. So the languages we use, like we use C and CUDA. CUDA mainly to improve the image processing and make them faster. And we use the Tickle and TK for our GUI. And we have also, like maybe you saw it, like we have an internal Tickle shell where users can actually use the Commandos in Tickle and our Commandos to do some image processing. So we do that in Tickle TK. And of course, we showed you some renderings. We do that all in C and CUDA. I just worked for the company just starting of 1st of January. So this was one of my first projects. I made a window editor, and that means actually that we can enhance, can change the contrast in the images. So I'll just show you, it's easy stuff, but then you actually know what we do, what the user can do in our software. Is it working?
This is not on the display. If you want to...
Can I move it in? Yeah, lovely. There you go. So here we have like an example image. I will just put the brightness a little bit up. What we use as a test image for the chromatic aberration, you can actually see that the red and the green channels are not lined up. Like you have a green blob and a red blob and they're not lined up. And you first have to deconvolve it. You can actually see the result on the left and you can really see like they're not lined up. So our software will line these images up and then you get like a better image. But another thing is like you maybe want to change the contrast. So we made like a widget that of course pops up on this screen and now pops up here. And you can just change by this curve the contrast in the window. So if we put it up really high up here, it changes. You can change that for every channel if you wanted to. So if you only want to change the red window, now you can only change the red window and the green window will stay. So here you can actually really see like we made the window in TK, Tickle, easy peasy, and then we transfer that to C code and then we have the image processing doing in the C code. So that's what we do. And of course, like this has to be understandable for biologists, so it must be pretty easy. Yeah, okay. Hopefully this. So we made as well some Tickle extensions. So we have an internal Tickle shell. What we have, you can actually see it here. So here you can type in any commandos that is available in Tickle. You can type in any, use also the images as a commando. So you can use an image and add another image. It's possible. And the good thing is like with Tickle, everything is hidden. Like you cannot change anything in the image. So that's really like the C part. So we separated those two things. So you can only change anything like the stats of the image and do some easy arithmetics. There you go. Yeah, of course not working anymore. So, and what we did, we registered the image names as Tickle commandos. So now you can do like if you have like an image 1, you can just say image 1 save to full 1 and then it will be saved on your computer. Or we have actually, if you want to add like 2 images, you can just do that, write it in the internal Tickle command and that's working. So this is what the TK we use for. So all the GUIs are made with TK. We use all the widgets. We extend some widgets. We use also like the tree window where you can just select window, select images as well. And we use, of course, the TK photo. So TK photo, what it does for us is we have a 2D pixel array, and we transfer that to photo, and the photo will be shown on the canvas. And this is something, that's actually not that fast yet in TK, and it's quite important for us because we want to make it faster. If it was to be faster, then the results will be shown quicker on the screen, which is always important. And of course, what we do also, we have like a movie maker. So you always have some sort of variables. You can change them. So you can actually make a movie. So you can have these renderers. You can rotate them. You can change the lighting, etc. And then you can just make a movie out of it. And of course, that uses the TK photo as well. So if TK photo is quicker, then renderings of these movies will be quicker. Our typical process that we mainly use namespaces. Every namespace is around 2,000 lines. Some namespaces, of course, get bigger and bigger. Namespace, most of the times, have 50 procedures. And we use like 1, 2, 3 arrays for the namespaces to store namespace variables. And we use a few objects. We try to make some objects besides having namespaces. But so far now, actually, we haven't figured out like what is the advantage for objects instead of namespaces. And that's something we want to figure out here actually. So we have like a couple of widgets and we have one window in an object. So this is like our typical use of Tickle. We have like a namespace. In this case, it's called myTool. We declare a global namespace variable VP, and then we store like all the parameters for the image. So in this case, we already set like the dimensions in the volume dimensions of the VP, and like with this procedure we can actually return the volume. So that's what we do. We get the VP, return them to the IM, and then we calculate the volume. So we have some questions from our side. For us it will be really helpful maybe to have the possibility to use OpenSceneGraph and OpenGL. If we could like if Tickle will be embedded or like can be using these things, that will be really useful for us. So we're curious, like, are there any developments on that side? Sorry, if this is a sensible topic. Okay. Oh, sorry. Fast TK photo is really useful for us because then the images will be shown quicker on the screen.
What do you mean with TK photo? Do you mean
the TK photo? So what?
Standard C
photo.
Yeah.
We have made, that is the interface between the low-level three-dimensional data is in C code somehow converted to a 2D array of RGBA data, and then the TK photo is used to put it on a canvas.
Yes.
So that is where the.
So like if we have a volume, what we do is like we can just, sometimes it might be useful to look like from this side in the volume. So we make an array out of that, and then we use that array to take a photo to the canvas. And often like the photo, take a photo is like the slowest part. So if it can be faster, it will be.
You could embed an OpenGL window with Paul's nice software, and then transfer it directly to the graphics card as text.
Yeah, we are looking for directions on what things we should start to try to use as a replacement of only using TK photo.
Yeah.
So
Sense of person to ask.
yeah, then we,
that's why we're here. So like, you don't know everything, so now we definitely would like to know more. And of course, like the problem we have, a lot of biologists have like screens like this, 4K monitors. And then you have, of course, the problem with like the fonts and the widgets scaling, like they're now more in pixels, and that gets really a problem. So I have here like an example, like this is like a normal laptop screen like this, and this is like a little bit bigger screen, and you can see like really that the widgets are like getting smaller, and if you have like a 4K monitor, then they really get small and they barely can see them anymore. So that's the problem that we are facing. So. Any questions? Yeah.
Sorry, the fonts must have built-in scales. System. Because you can, I think you can control as a global setting, the factors that are used to, I think it's TK scaling. You can use that.
Yes,
Yeah.
on the wiki we found some advice that you need
you have to
upon
make sure that your fonts are using
upon initializing
using point sizes, not
yeah.
pixel sizes.
Yeah, we should be converting everything away from using real pixel numbers to points.
Yeah, and then you just
yeah.
change that, and then that will fix that. You might have to do some extra work to make the widgets work nicely with that, because I don't know that they will cope very well with that. I mean, this is something which we may have to address. But that's that might actually be something we can fix it.
Yeah, cool.
On the other hand, you've got the right person for 3D, you've got the right person for objects. So
Lovely.
Like if you're using fonts with dot sizes, you will have the exact opposite problem, because your font is increasing in size, but if you're using embedded bitmap images, your images will get smaller and smaller and smaller compared to the font. So
you have to work out what you
I think that there's no solution without any additional work.
Okay.
I think there is a solution without additional work. I think you can do some things relatively easily. Changing the fonts is one of the most.
Cool.
You have shown that contrast editor.
Yeah.
And how does that work, the interactivity of it? Is it a TK canvas with some elements, or is it all one single TK photo and you do all the interactivity on the side?
We do that in, it's called window plot. We had, like, I'm not sure, we had it already in the company, but it like we didn't make it ourselves. So we have something that's called window plot, and that uses indeed like there's a frame and a canvas, and it actually draws the curves and the lines on there with TK. And then we could just add indeed like dots, and that they actually like but the thing is like. The calculations between the dots, we just use math. So we use of course a spline for that, and then we can just like make really like small segments, and then we can just combine them, and then we have like the line, the curve.
But so this feature of moving the curve around, that is done by bindings on canvas elements.
Yes.
It's fast enough.
Yes. Indeed. So indeed, like I have a dot. That's indeed an element. I bind. Indeed, like if you on the dot, then you can actually move it, and it will recognize that's on the dot. And then it actually uses also like, because there can be multiple lines on top of each other. So if it's not on the dot and you click on it, so it has to produce a dot, and that has to do that for all the lines that are on there. So that's actually it's going quickly enough, and then it has to move to the dot, and and all the dots that are behind them as well. So that's how it's organized.
I'm a bit surprised that the sharpening you showed works so seemingly perfect. I would have expected to appear aliases, some kind of artifacts generated by the algorithm. Didn't you ever experience such a thing?
Well, the most important thing is that we have like this microscope. And due to the lenses, that's what this blurring is going on.
Yeah.
And we have a theoretical model how this blurring is going on. So it's not that we have like an image and we just enhance it. No, we have a model how actually this blurring is. So that's a really important thing. So what we, of course, but still you have noise. So that's the goal, is you want to minimize the noise. And therefore, so that's kind of important. Like the information is in there, it's only not on the right location. So so that's why we don't get that many artifacts.
But the modeling needs to also have input on what is the expected amount of noise and the type of noise. So
And like
the noise is also modeled to get the maximum amount of information that is in there out. But if you don't do that and you just do a sharpening, which is like a high-pass filtering, then it would produce indeed a lot of artifacts.
Yes. So also what we do is like what you can do with a microscope. You just like make a picture of like a 1 point, and then you get like a blurred image, and so then you actually know how this blurring occurs. And the good thing about the blurring is like it doesn't depend on where it is. So that's what we call like a point spread functions. You get like from one point you get a spread function, and with that you can calculate it back all the other images because they have the same settings. More questions?
So if there aren't any further questions, I would like to thank Frans and Paul for. We will then now.